because you just saw with 20 millimeters mesh size, it's not gonna get you anywhere. It's wrong, it's off by more than 50%. It's just bad. Hi guys, welcome to module 2 of the Inspire course kit. So today we are going to take a look at this module, which is structural 2D. Now, structural 2D is similar to structural 3D, but the question may arise, why do we even bother to use 2D when we can all use 3D? The thing is that you would care with element size. Just imagine you would have something like a thin plate, right? So it's something like this. And this is also the more or less the tutorial here, or the model which we will be using. So just imagine you would have something like a fixed line here and a force pulling here, and this would be a very thin plate, right? So one dimension in space is much smaller than the other two. If this is the case, just imagine you could either do 2D mesh like so, more or less, right? Or if you just would zoom in on that, let me just quickly catch my pen here to draw it a little better. So just imagine this would be a section like from here. Then if you would mesh it in 3D, because you would want to have a certain amount of elements over the thickness, you would get a lot of elements, and it doesn't really help you too much with accuracy. So the 2D mesh can be as accurate as the 3D mesh with a fraction of the elements. So that's why you want that, because this allows you then to be a lot finer, a finer mesh where you would care, compared to if you would have a 3D, you will get at the limit of your computation power pretty soon, or you would have to pay a lot for, I don't know, cloud cost or something like that, which is not really necessary. So simplifications like this, going to a 2D mesh, is a great technique and should be used and applied if it's possible, right? So always check if it's possible to do those. It does not make sense to try to mesh a cube-sized object where you have dimension 1, 2, and 3 with similar sizes with a 2D mesh. I mean, you could do, right? You could just extract a mid-surface and then do elements here and assign a thickness like so, but it would not really be a good approximation of the real geometry. So you could say that whenever you have the case that one dimension is rather small compared to the other two, then you should consider a 2D mesh rather than doing a 3D mesh. And this is what this lecture is about, right? So let's dive in. We have the lecture here. So this is the file you have. You have a video going over how the steps are with text annotations. Then you have the instructions, which is also pretty cool because you can then just get a glance on what the results would look like. And then you have an input model, which you can just drag and drop on here. And you have also a solution model in case you want to check that. Okay, now let's see. Basically, what I would like to show you first is the slide of the introduction. So just that we get a glimpse of what's in here. So we see the model, right? We have 40 millimeters of diameter a hole here. Then we have 120 millimeter, that would be the width, and the length would be 500, and the thickness of the plate would be 3 millimeters. All right, then we have a 20 kilonewtons force applied to one side and the other side is fixed. And then it tells you about something like an analytical solution. And this is found on this location. So I went there and just entered the parameters just to make sure that I don't tell you something which is not correct. And did I close that now? No. That should be here. Okay, so you can go to that link and just fill out the same values as I did here. And you will see that you have the same values here. So the concentration factor of 2.3 and the maximum stress of 192.02 megapascals. And that's the same values as you will find here in this table. Okay, so we just got the correct solution by just looking at the analytical solution, and we already know what the FE should tell us. And this is an important consideration, to just get a feeling or understanding, or in this case, get the truth before you even doing your simulation. Because simulations can lie to you. And you will see that in a minute. Okay, so I would say let's jump into the model and just see what we are getting here. So you see there's already a support setup. You can click and check that. So you see at the bottom right, bottom left, you see that we have all constraints which are fixed here. And then we have a force on the other side, and we also can click the force and go into the left, bottom left, and see it is 20 kilonewtons. And also make sure to not make the mistake and think that if you just enter 20 kilonewtons here, you don't have to check this anymore. It will always just have the direction vector here, not the actual magnitude of the force. The magnitude of the force is defined up here. So this is a common mistake I see students do, entering something, or don't care about the field here and just thinking that if I do 20 kilonewtons in X direction, it will respect that with the direction vector. It does not. So the direction vector is scaled down to a unit vector and then multiplied by the magnitude you have up here. All right, so that's important to know. But basically, you see it's just one load case with the set constraints. You have the support, the force. You could check the material. That should be default steel. And that's that. So you could, without further ado, just run it and see. I did do a couple of tests, but let's just run it for once that you see how it's done. Gets on the other monitor. Okay, so this would be the field. Now you could say, for example, here 20 millimeters. And here, this selector is important. This selector changes between different element formulations. So you have different orders of the element formulation. Either you have a first order or a second order. Those two are implemented. And this means if you have a first order, then the strain between two nodes remains constant. Wherever with second order, you have a mid-side node, so an additional node, and then stress the strain could vary between those two nodes. So basically, the more accurate or second order element formulation is the one which is recommended to use if you care about the stress, and it would converge faster to the correct solution by decreasing the mesh size. If you don't 100% get what I mean by that, don't worry, we will see in a minute a graph which just points that to you in a very detailed way. Okay, so but stay with me here. Faster means that it will take less computation power, but it's also less accurate. But for our case here, faster is all right for the first considerations. And let's just say I go with 20 here. 20 millimeters would be the element size. Let's get a feel for our model. So like 20 millimeters is about that big, right? So this is also a good way of just getting to know what this is. This is a very, very coarse mesh. And this coarse mesh will lead to bad results, for sure. But I just want to show you how bad they are. So faster, 20 millimeters, everything else can be on default values. And I press run. And it will run like so. If you don't have the element size property here, it is very much likely that you have the SimSolid solver selected. And you could reverse this selection by going to File Preferences, and then you go to Run Options here, and then you see OptiStruct. This should be OptiStruct. If it's not OptiStruct, then you should change it to OptiStruct. Okay, it's doing its thing. It's solving our case. That should not take too long. Let's see if I don't have any mesh override. Yes. Okay, so 20 millimeters should be respected. I could already check also in the Open Run folder and see what it's doing. So it's still in the meshing phase. I know that because I don't see a .fem file. If I'm seeing a .fem file, I know it's already solving. And so in this case, it's just doing the meshing. And we could also check, for example, mesh input files here. You see now the .fem file was created. It's very small, so I would expect a rather small time to solve it. And indeed, it already solved the model. So I open that and I see the displacement. I'm interested in the von Mises stress, and you see very coarse mesh. All right, let's check min-max. So the maximum stress is at a correct location. So I would also assume it would be on one of the two sides, up or down. But it has 90.9 megapascals. And let's compare that again to what we have with the analytical. So it's less than half of it. So pretty big change. And now to save you some time, I did a lot of runs, and it's also in the instruction page. But I did go a little further even. You can also see that here for different element size, the thing was run, and then you can see how it's changing with the stress values. But I just wanted to show you one thing. I did just one. I did it just for first order element, but it would look more or less similar, I would say, in the second order. All right, what do we have here? So this would be a mesh convergence study. It's pretty standard in industry to do something like this, and it's not gonna get you anywhere. It's wrong. It's off by more than 50%. It's just bad. Okay, so this is our starting point at 20 millimeters. So basically what I just then did is run with 10. Okay, it increased. Whenever you see that the stress is increasing by a considerably margin, then you just keep on decreasing the mesh size in this area until you get to a converged state. And this is what you see here. By the way, pay attention to that the x-axis is scaled logarithmically, because it would look a lot different if I would do that with linear scaling. You would not see a thing here. So that's why it's better to go with logarithmic scaling on the x-axis, being the element size. Okay, so 10 millimeters, it increased. Then I think this is 4 millimeters, it increased. 3 millimeters, it increased. Here you could argue, well, it doesn't increase that much, right? From 152 to 158. You could think here that it might converge out at 160, but that's why it's important to keep going. So basically here is the thing for 1 millimeter mesh size, 180. Then 0.7, 184, 0.5, 186. You see, we're not there yet. 192 is the truth. And 0.25 and then 0.1, right? So 0.1 at the minimum element size gets you around the area. So, but this is a bigger model. You must know. Let me see if I have that still. Should be one of those. Yeah, you see 113 megabytes of disk memory for the very, very small model. Let me just quickly show that how this looks, because you need a little bit of a technique there to get that even running, because if you say that you want to have everything with 0.1 millimeter of mesh size, it would kill your machine, more or less. Except you have a monster of a machine, but I don't. And so what I did is I just created like a partition with geometry partition. And then I just said, okay, I think my default mesh size stays at 1 millimeters, but I have said that this surface here, the partition, has a mesh override, and up here, you see that I defined a 0.05 millimeter minimum mesh size, and 0.1 being the average on that surface. And so what this gets me then is, let me see if I can get the results back here. I hope so. So that would be Is it that? No. This is fine, or is it? Wait a second, let me just quickly check. (0.25). Well, okay, for this example, it doesn't matter if it's the 0.25 or the 0.1 model, but you see the difference, right? It goes down here. It still has a lot of elements, but you can see then that the von Mises stress is a lot higher. Here was the 189 megapascals here, but you see there's a lot of elements, and it takes more time to compute those. So in this case, I think a couple of minutes. Still alright, but you can think of bigger models needing a lot more time to converge solutions like this. Okay, so what to take from this lesson? I would say you should definitely know about mesh convergence studies, because they're very important with mesh-based solvers. And this graph, to just see what this method is, to start at one random point and then just decrease the mesh size wherever you have a hotspot. Hotspot means that you have a maximum stress at a location you care about, and then just decrease the mesh size there until it does not really increase too much. So I would say around here you could say it's converged more or less. And if you see the 1 or 2 or 3 megapascals, they might not make that much of a difference, but just assume you would have something close to 150 as a yield stress, then you would be really in a bad situation if you just said, all right, 150, it converged, and be done with it. So I think that's the most important thing to take away from this lesson. Besides, then from Inspire perspective, you should be able to load in models like this for sure. You already saw constraint and force creation in module 1. Here I would say the only other thing which is important here is if you have a surface and want to have the mesh defined here, you have this mesh override functionality where you can just see how you do this, and yeah, and then just define I want to have a specific mesh size in exactly that area. Besides that, also Inspire perspective, if you want to see the mesh, you should just click here, right? So you should know that with Inspire, you see the mesh only when you run it, right? Because the meshing is done when the solver runs. And before that, you cannot see the mesh. And that's a contrast to HyperMesh, because in HyperMesh, you can see the mesh before you click the run button. But here you have to just click run and then go into the input folders just to see the results and check that and click that button and then just see the results. But that's also very important that you check the mesh and just don't think that if you have pretty looking gradients on the stress, then it will be all right. Just make sure you understand how the mesh works, do the mesh convergence study, and you should be good. So I think that's the biggest takeaway from here. And then just out of curiosity, let's just see quickly how would the SimSolid solver have performed here. There's no mesh here, so we can just click on run. Yeah, sorry, I forgot that. SimSolid must have a solid part. So whenever you have a SimSolid option, you cannot run that on a 2D mesh. But just because I'm curious, let's say I would just use this and wait a second, I will do something different. I will drag in again the ST-mod. Now I have it double. Okay, new model, and drag it again in. Okay, what I like to do is just drag this out by 3 millimeters. So I have that. And now here the constraints I have to redo because it's going onto the edge and I just don't want this, but I want the complete surface to be affected. So I will redo the constraint, and same goes with force. So that should be 20 kilonewtons. I cannot edit this, right? No, okay, just there may be an option, but I'm too lazy to look for it right now. So whole surface 20 kilonewtons, and it should be in the other direction. Okay, Now let's see what SimSolid would get us, right? And how fast. You see, instant. And now let's see the von Mises stress. Well, pretty close. 189.8. So 190, I would say. Well, I think forget about the display. That's not really... yeah, well, it's not that the gradients look a bit strange, and also the geometry looks a bit strange, but the value, if you just look where SimSolid would be, 190 is pretty close to the actual solution, right? So you're up here. And that's instant, and I think the model here takes around a couple of minutes to run, maybe 5 to 10 minutes or so on a medium desktop PC. So just keep that in mind, that SimSolid can be also a quick alternative to just see some results fast. And also don't worry too much about the mesh convergence. All right. That being said, I hope you enjoyed the module 2 of the Inspire course kit. If there's anything you would like to know, or if you would like to offer some constructive criticism or anything else, just leave a comment down below, and I see you guys in the next one. Bye.